So what are the algorithms that we use? We usually have an objective function, and in machine learning and deep learning, that's a convention that you like to minimize. You want to minimize the loss function. You want to minimize your cost. This is equivalent sometimes to maximizing the likelihood, but here we want to minimize the loss function. The thing is that this loss function is coming from huge data sets. The problem with loss functions that are coming from huge data sets is that it's gonna be very expensive to evaluate them. That's why in deep learning, you take a look at mini batches of data. And if you take a look at mini batch of data, you're doing your summation on a subset of your data. It means that you always have access to noisy estimates of your loss function. There is usually a summation over your entire data set, but now you're doing your summation over a mini batch, over a subset. That's why J, we are using it to denote an estimate, a noisy estimate of our objective function. And usually this noise is coming from mini batching. We are gonna do gradient descent to optimize our loss functions. But because we are using a noisy estimate of the loss function, that's why it's called a stochastic gradient descent. Always your gradients are gonna be approximate. They're gonna be a stochastic. They're gonna be noisy. So this is gradient descent. The parameters of that deep model, these functions f1, f2, fl minus 1, and fl are parameterized by a bunch of weights and biases, usually. And we call those parameters, we put all of them in a list, and that list is gonna be our theta. And we take gradient of our loss function, or the estimate of the objective function. That's gonna be our gradient sitting here. We take a tiny step in the direction of the gradient, and then we keep going down. Basically, we are going downhill, and we want to find the minimum. This is the learning rate. That's the direction, and you are doing gradient descent. Because of the negative sign here, you are descending, and it's stochastic because you're using J here rather than L.
Can I ask you a quick question about J?
Yes.
So J is an estimate of the objective function because we're only training on a subset of data. Is that why? Or within that subset, are we doing something else?
So it's an estimate because you take a look at your data in mini batches. Let's say you are doing mean squared error. That's your objective. And let's say you are doing a regression.
Mm-hmm.
If you are doing a regression, you are doing a summation over your entire data set of the errors that you are making, of the square of the errors. Okay? But now that's your L, the summation over your entire data set. J is gonna be a summation over a subsample of your data set. Maybe
and that would just be a random subsample?
Exactly.
Okay.
So that's gonna be a random subsample of your data set. So per each iteration of your stochastic gradient descent, you subsample your data set. Let's say your data set is 1 million numbers. Out of those millions, per one iteration, you take a subsample of 256. That's the size of your mini batch. And then you do the mean squared error on that subsample on 256 data points. So that's going to be a noisy estimate of your loss function. And per each iteration, you subsample a mini batch.
Okay, thank you.
There is a question from Brandon. Do you always want to do random batches, or can you do sequential batches for any reason? There is usually a summation of the errors that you are making per example. And why is there a summation? Because the underlying assumption is that your data are IID, independently and identically distributed. So your data are independent from each other, and they have the same distribution. I don't know, in the case of regression, you are making a normal assumption or a Gaussian assumption. All of your data points are Gaussian, and they are independent. Because they are independent, you have a product in your probability, in your likelihood, but then you take a log of the likelihood, that's going to give you a summation. Because log of product is the summation of the log. Okay. That's why you usually have a summation. And you want those batches to be random because of the independence assumption. You want your samples to be random batches. So yeah, Matthew, that's where I was going with the next part of Brandon's question. Can you do sequential batches for any reason? There is this idea of curriculum learning where you want to feed your algorithm the hard examples. For instance, you can do hard example mining. Maybe your algorithm is really good at solving simple examples, but then it's making mistakes on some hard subset of your data set. That's what people call curriculum learning. So that's gradient descent, now that we have an understanding of it. Then we are going to do backpropagation. You have a loss function, J, or an approximate estimate of your loss function. And let's say your theta is d-dimensional, and your loss is a single value. It's usually the case. Your loss is a single value. So your J function is going from RD to R, from d-dimensional stuff to one-dimensional stuff. The cool thing about backpropagation, I have a tutorial online. I'm not going to go through backpropagation in this course, is that you can take derivatives of such functions very easily. It's very cheap to find a derivative. It's as cheap as a forward evaluation of your J function. You get the gradient of J from RD to RD. So that's what the gradient is. It's a function from RD to RD. And it's one backpropagation, and it's super fast. Some people might say stochastic gradient descent is stupid. You're just taking a gradient of your loss function and then you take steps in that direction. That's a stupid algorithm. Why don't you use more smart algorithms? Why don't you use second order derivatives? Why don't you use Newton's method? It's second order. You need the Hessian then. And what is the problem? The problem lies in backpropagation. if you want to compute the Hessian, which is a function from Rd to the matrices, because a Hessian is a matrix, you need to do d iterations of backpropagation. Then that's slow. Computing these J functions, because these are deep and wide neural networks, are expensive, let alone doing it d times, and d is usually in the order of millions of parameters. That's why second order derivatives and second order algorithms are out of the picture when you do deep learning, when you do training. So we have to live with first order derivatives, only gradients, no more Hessians. So if that's the case, then how can we make gradient descent faster? There is this idea of momentum, where you say in the previous iteration, I had a velocity. I'm gonna keep that velocity, multiply it by a number. Maybe I'm gonna keep 90% of that velocity. That's gonna give me some momentum. Then add the new gradient with our learning rate. That's gonna give us the updated velocity or the new direction. And we take a step in that direction. It's as if you're rolling a ball in a valley, and then the ball, as it goes, it's gonna add momentum. So this algorithm is gonna make gradient descent faster, but it's a little bit careless because you might miss your minima. You might jump over it because of the momentum. You're going too fast. That's why people came up with the idea of, it's actually Nesterov who came up with the idea of Nesterov accelerated gradient. The idea is that rather than taking your derivative at the current position, look ahead before you make your decision, before you commit. What do I mean by look ahead? Forget about this part. You have theta t plus 1 is equal to theta t minus gamma vt minus 1. So you look ahead, you put that term here, that's where you evaluate your gradient, and then you make your decision, you compute the gradient. That's when you make your decision to commit. Then that's gonna be your gradient, your new gradient. This is more prudent because now you're looking ahead, updating your gradient, and then adding it back to your momentum. And that's gonna be your gradient descent. That's gonna be the direction that you want to move towards to update your parameters. So it's always a good idea to look ahead and then decide, rather than decide and commit now and then do our actions. That's the intuition behind Nesterov accelerated gradient. So what I'm talking about in these slides are writing your compiler, which is basically, most of them are based on gradient descent. And in the deep learning literature, it's usually one of these algorithms that they use to train their models, to train their deep models. The next algorithm is AdaGrad. What is the problem with what we saw so far is that the learning rate, you have to set it yourself. You have to choose a learning rate and live with it. And usually the way that you set these parameters, usually these are called hyperparameters of our model. Whatever that has to do with the compiler is our hyperparameters. the way that you set it is usually using your validation data set. So far we talked about training data set, we talked about testing, and then the hyperparameters are gonna be set using a validation subset of our data set. And the validation, you look at your, I don't know, metric, your evaluation metric, which could be your accuracy, and choose whatever learning rate that's gonna give you the best accuracy on the validation data set. And once you do that, the next step is testing. And then the next step is putting your code in production. So the way that you set these lambdas, eta, is that you train for multiple times. One algorithm is grid search. You put a grid on this learning rate and then find the best one. That's the fastest, and that's giving you the most accurate result at the end of the training. And as you can see, this is not cheap, because now you have to train your model thousands of times to find what is the best learning rate. It would be good if you could make the learning rates adaptive. The rest of the methods that I'm gonna cover are trying to make eta adaptive, the learning rate to be adaptive. For add a grad, this is just our gradient. Let's call it G. That's our GT. The idea is that this is the same gradient descent that you have here. It's theta t plus 1 is equal to theta t minus our eta is now adaptive times the gradient. But how do you make it adaptive? You take a running average. It's not actually a running average, it's the average of the gradients multiplied by each other. So if your gradients, see your gradients could be a matrix, and the entries of that matrix are from time 1 up until the current time. That could be a matrix. We don't care about the matrix. We care about the diagonal of that matrix over time. And these are just gradients per each time. And then we are multiplying them pointwise. That's what the circle dot means. These are vectors. As you can see, the gradient is a vector in RD. It's d-dimensional. There are various ways of defining the product. Here, the product is every entry squared. That's what we are doing here. There is a square term in G. That's why you do the square root of that square term. That is trying to give us an adaptive learning rate now. And it's adapting to the previous gradients that you saw before. If we were in class, I would ask, what is the problem with this method? And can anybody answer? What is the problem with this method? Yeah, the question is, we still set an initial learning rate. That's correct. You set an initial eta, but that's gonna adapt. As you go along the method, it's gonna keep adapting. So this method is less sensitive to learning rate compared to gradient descent. But that's correct, you still need to set an initial learning rate. What is the other problem?
We'd have some problems like numerically when the gradient becomes really small.
That's a good point. That's why you have this epsilon term here. And this epsilon is usually set to be 10 to the power negative 8 to avoid dividing by 0. So any other problems that you see?
Is it less efficient as we continue to learn and learn because the sum over all of the taus gets longer and longer?
That's a good point. So g squared is a positive number. And you keep adding positive numbers together. So this g is going to grow. And towards the end of the training, this g is going to be very huge. It means that your learning rate is going to get smaller and smaller. And in the end, you are not optimizing at all. Basically, that term is going to be 0, and then you're going to be stuck. So the algorithm is going to stop prematurely. So what can we do to fix it? You can keep a running average rather than averaging over from time 0 up until now. You can sum the most recent gradient squares. And that's the idea of add a delta. And I'm going to say why it's called add a delta in a short while. But add a delta is going to do a running average of these gradient squares. So if you think about it, you're doing a running average. You keep gamma of the previous average, and you add your new gradient square. That's going to give you the average gradient. You do the same thing for updating. You say, this is just defining what is delta. Delta t is theta t plus 1 minus theta t. That's the definition. Nothing special there. And then you set your delta t, which is this term here, to be eta divided by your running average rather than the summation plus epsilon. The problem is that with add a delta, the units don't match. This has a different unit compared to eta. You keep a running average of your delta t. And then the update of your delta t is going to be that running average, root mean squared error, divided by the root mean squared error of gt times gt. This term here is just the root mean squared error. And that's going to be your delta t, and that's going to be adaptive at a delta. And the cool thing is that now you don't even need to set eta at all. Eta is gone. I think we are over time. If any of you want to leave, you are more than welcome to leave. And if you have questions, for those of you who have questions, you can ask questions.
You had mentioned a tutorial about back propagation, and I'm interested in that. Will that be linked on the online?
I can send you the link to that tutorial to back propagation.
That'll be helpful.
I'm sorry, I think I missed it when you said it, but what's the target looking operator in Adagrad or Adagrad?
Say it again.
What is the target like operator in Adagrad, the circle with the dot inside? What does that denote?
This dot inside is element-wise products.
Okay, so it's just a dot product. Okay.
It's not a dot product, it's element-wise. So you have two vectors here, and you're multiplying them one by one. The output is still a vector, it's not a number.
Oh, the output of that's a vector.
So
oh, I see what you're saying.
So
yeah. So you take it. Okay, yeah, I got it.
Yes, so Blake sent us a link, and thank you. It's the Hadamard product. So you're doing point-wise operations on your vectors.
Okay, I see.
So these are element-wise squares, element-wise products. If you have x1, x2, x3 up until xn, and you have y1, y2 up until yn, you are doing x1 times y1, x2 times y2, and in the end, xn times yn. Any other questions? So there is a question in the adapt delta method, what is g squared? So g squared is exactly what you see here. Again, that's element-wise squared. If you have x1, x2 up until xn, that's your vector, then it's going to be x1 squared, x2 squared up until xn squared. The output is a vector still. So E is your expectation, is the average, is the running average, and it's just a notation. The running average of g squares at time t is equal to gamma running average of g squared at time t minus 1 plus whatever that you get, whatever gradients that you have now. Okay, perfect. Any other questions?